Welcome PDC 2003 attendees. I'd like to thank everybody for making it here today despite all the fires and everything else. I know myself, I almost didn't make this talk, but I'm glad I did. My name is Kang Gatlin. I work as a program manager in the Visual C++ team. What I tend to focus on is code generation and optimization, and this is what I'm going to talk about here today. Now, this is my first PDC, and when I was first putting together the slides for this talk a while ago, somebody saw the slides and they commented, "It looks like a PDC talk." And at the time, I thought that was an odd comment since there was no context. And he said the reason was that it looked like the type of slides that a PDC audience would appreciate. So I thought about that and tried to figure out what exactly will be the group of people that attend this talk. So through my research, I was able to construct the top 5 reasons why you're at this talk. And I think this, to some degree, summarizes the class of people that will be here and get some benefit, although I think it has wide-ranging benefit. The number 4 reason is that you're the type of person who looks at their inner loop, says it should take 4 cycles, you run it through your profiler, it takes 6, and that gets you upset, actually. The number 4 reason is you're the wolf on your team. You're the person, when performance counts, the people in your company, the people in your group, go to you for the answer, because they know that if there's somebody who can get the extra 5, 10%, it's going to be you. The number 3 reason is you realize that saving 10 seconds for 1 million users is 115 days saved. So the 10 seconds may seem insignificant, but you realize taking the extra day to get that 10 seconds out is a huge win. Furthermore, if that 10 seconds is compounded each time they use the application, multiply that factor out. The number 2 reason is you like to read Itanium assembly for fun. Enough really said there. But the number 1 reason is that you care about generating good code. And this is what Visual C++ does. So here's the agenda. I'm actually not going to spend time going down the agenda. I'm just going to dive right into the talk, as we don't have much time here at the talks. So first, I'm going to open with a quick refresher. And I'd like to just open with a couple of bullets about some things that probably a lot of people know, but through my interaction with people, I've discovered a lot don't know. Number 1, it's okay to use /O2. I talk to a lot of people. They say Microsoft doesn't use /O2. That's not true. It's used for the OS. It's used for the compiler. It's used for Visual Studio. We run the same regressions. It's very reliable. There's a lot of places to use O2. And if people are interested in talking about that, you can always grab me after the talk, and I can go into more depth. The other thing that a lot of people don't do is use /GY. And this is to generate comdats for individual functions. This is generally useful. And it's the type of thing that we should even consider making default on. Right? The cons with this, though, is that it generates slow link time. The wins with this is it exposes more opportunity for the linker to give wins. Additionally, as a little side note, many people want to go ahead and do release builds with debug info. So you'll go ahead and throw /debug. If you're going to do this and give this release out and expect performance or want performance, make sure that when you throw /debug, you additionally throw /incremental no, throw /optref, and opt-ICF. What opt-ref allows the linker to do is eliminate comdats with no references, and opt-ICF allows the linker to do identical comdat folding. Again, this is all review here at this point. Additionally, more review, going back to what we did for the last 2 releases with respect to code gen, In VC 2002 and VC 2003, we did quite a bit of work in improving performance. One of the big things we did is we added support for the Pentium 4. Here you throw the /G7 switch. If you don't throw this, the default is blended, which actually in turn defaults to /G6. We also added support for SSE2. One thing to note about this switch, though, in contrast to the G7 switch, is if you run the code generated from the Arch SSE SSE2 switch on a machine that doesn't support that instruction set, you'll most likely crash. Whereas with G7, you can run it on downstream platforms. The next big thing that we did in the past revisions of Visual C++ is we added support for whole program optimization. The basic idea here is you want to do code generation on all of your files at once. So what's the standard model for doing compilation? You give me a CPP file, I run it through the front end, I run it through the back end, I generate an object file. What if I want to do inlining from one CPP file to another? The standard compilation model, you're generally out of luck. With whole program optimization, we're able to take all of the .cpp files, generate .obj files. These .obj files are distinct from the traditional .obj files in that they contain IL, not to be confused with MSIL. This is the IL that the front end passes to the back end. And from this, we can do additional optimization, such as inlining across files, better custom calling conventions, smarter stack alignment. In Whidbey, we've done work to improve this. And in fact, at this point, you can kind of view the talk as the transition between the old refresher and now the new stuff. So as I stated before, we had whole program optimization in the past. Now we've improved it. So what you see right now on the screen is just a simple call graph. At the top is the root. At the bottom are the leaves. And I know that makes no sense, but that's the standard terminology. And in this, what you're looking at is the call graph of a whole program. One of the things we've added in Whidbey is a new analysis feature called bottom-up, top-down analysis. So in the bottom-up phase, what you do is you start at the leaves of the call tree, and you work your way up. As you do this, you're doing several things. One thing you're doing, and probably the most important, is you're doing what I call creating theorems. You're looking at the code, and you're asking, if I could make a particular statement about some property of a variable or an expression, can I optimize it better? And you're going to create these theorems and set them to the side. Additionally, you'll push up information such as which globals are changed, or if a pointer is only dereferenced, in which case you can also send this information back up the call tree. In the top-down phase is when you begin what I like to think of as the theorem proving stage. So I've created all these theorems in the bottom-up phase. Now what I do as I go top-down is I now attempt to prove them. And if I can prove them true or false, I might be able to do those optimizations that I spoke of. So let's make this a bit more concrete, and we'll look at a very simple example. So here we have two functions, foo and bar. So foo calls bar. Bar is this function that does a memcopy from B to A. As you do the bottom-up analysis, you can ask yourself this question: are A and B aligned? Because if A and B aren't aligned, you hit the obvious problems that either you end up having to do one-byte copies, maybe pay the cost of unaligned data moves, or go ahead and doing the fix-up so that the data is aligned and do the memcopy. If you know that the data is aligned, you can go ahead and chug through doing large block copies. So you ask this question in the bottom-up phase. Now in the top-down phase, you can effectively begin answering questions. So in foo sees this question. Are A and B aligned, the parameters called into bar? Foo sees they were allocated on the stack by the compiler. Foo can answer, yes, they are aligned. We can now do the nice code gen for bar. Actually, one other thing I should note is that we also know that foo is the only function that calls bar through the use of this. So this is a very simple example, but it's indicative of the types of things that we can now do. So you've seen that there's a lot of power you can do with creating the theorems, and proving the theorems, and many statements. But the problem is if you have static code doing analysis on it, it leaves a lot of open questions for the compiler. For example, I have two simple code snippets, and you ask, how often is A less than B? Unless you have additional information about A and B, you have no way of really answering this. In this for loop, we have this iteration from 0 to count, or rather count minus 1. And again, you hit the same problem. What is a typical value of count? Is count usually 1,000,000? Is it usually 1? Without more information, it makes this hard to determine. So we've added this new feature, profile-guided optimization. And what we do here to help the user is we instrument code through the use of probes. So we place these probes into the code to get more information about their application. And we write this out into a profile database. Now, there are two main types of probes. One type of probe is the value probe. And this would be used, for example, in the for loop that we looked at. The value probe will construct a histogram of the different values a variable can take on. So as I noted before, we would use it for the for loop, the count value. We also use it, for example, before switch statements. Another type of probe that we have is the count probe. And the count probe is used to count the number of times you go down a particular path. So if you lay out the basic blocks of a function or of a program, you can imagine the count probes are sitting in between the edges of the basic blocks. Now what we try to do is we try to get the minimum number of probes into the application to get full coverage. The reason we do this is to minimize the cost of instrumentation. I do want to make one thing clear, though. The code that we instrument is not the code that you ship. You instrument your code, you generate your profiles, and from this, you ship the optimized code. So let's take a quick look at how you would build a profile-guided, optimized application. So the first phase is you take your sources, you compile it with the /gl switch. And this is the switch you've used since 7.0 now to do the whole program optimization and the link time code generation. This generates the object files. And as I noted before, these are not your traditional object files, but these are the object files with the IL in them. The next phase is you take these object files and you link them with LTCG:PGI. PGI stands for Profile Guided Instrumentation. And this will generate the instrumented image. The next phase is you now take your scenarios. These scenarios should be as representative as possible to the real-world scenarios for your application. One of the common mistakes we see is people think that this is meant to be code coverage. Absolutely not. It's meant to be the scenarios you expect your users to use. You run those with your instrumented image, and you get as output, of course, the output from your application, and you get the profile data. You now take this profile data and the object files that you created in the first step of the phase when you compiled with /gl. You then link that. This time, instead of with LTCG-PGI, you will use LTCG-PGO. This stands for Profile Guided Optimize. And the output is an optimized image. As you see this, you probably note there are build lab implications for this. Currently, your build lab is probably set up to do a release build, maybe a debug build, cranks them out, and you pick them up the next day. Now you have to go ahead and do the instrumented build. Your build lab will also have to crank through scenarios and then produce the optimized build. It's just something to keep in mind. So in the demo, what I'm going to do is I'm going to take this call tree. It's main that calls 3 functions. It calls safety, it calls risk, it calls pricing. And we're going to pass it parameters such that it calls risk 10,000 times, but it calls safety and pricing 1 time. And what we want to note here is, given this extra information, what Pogo is able to do with respect to optimizing it. Okay, so I already have the solution loaded, and it's a basic 1CPP file. And I'm actually going to show you how you would do this through the IDE. Additionally, some of you may already know, if you download the platform SDK, we actually have command line Pogo support for Itanium in the platform SDK. It's a little bit more difficult to use because it is command line, but it's probably what the build lab would use, and I know a lot of developers also do use command line as well. So first we'll go to build, and as you can see now, we have the profile guided optimization item. We'll select that, and here we'll select instrumental build. It built successfully. After this, we'll now go back to build again, and this time we'll go to profile guided optimization again, and we will select Run Profiling Scenario. So here you'll get a box that allows you to enter information about the command you wish to run, the command line argument, any environment variables you wish to set, if you wish to merge the environment, and of course the working directory you wish to run the scenarios in. So what we have here are the command line arguments for the application. And what these numbers simply represent are the various edges on the call tree that we looked at. So we'll run this because we want to create this particular call tree that we had looked at. The scenario has just run. We now go to build again. We'll go to profile guided optimization. And now we'll select do an optimized build. So what this will do is it will use the profile data that we just created to do an optimized build. After that, we'll simply go ahead and run this application. And it's a simple console application, and hopefully this is viewable for people. What we see here is we've printed out the addresses that each function gets invoked from. So we see that main is called with the address 401879. And we also note that the address from risk is called with the same address as main. That's because it was inlined. Likewise, reward was inlined into risk, which was inlined into main, and analysis was inlined into reward, but only when called from risk. And this is because of the call tree that we had looked at. So let's go into a little bit more depth about the actual optimizations that are taking place with Pogo. And this will also help better explain exactly what we've seen. So first, inlining. Now, profile-guided optimization uses call graph path profiling to do the inlining. So here I give an example call tree, again, A, foo, bat, all call bar, and baz. So now let's generate the profile data for this. And we end up getting these types of edge weights. What we see is bat calls bar a lot, and baz is called a lot by bar, but only when called through A and foo. So what's the appropriate inline strategy here? With profile-guided optimization, we can make the inline decisions at each call site. So we can inline baz into bar only when called by A or foo. We won't inline it when called by bat. Additionally, we can inline bar into bat, but we don't inline it into any of the other functions. Another optimization we can do is switch expansion. Now, as I noted before, we have the value probes, and this is where a value probe would be used. So we have a switch statement that looks like this. And with our profile runs, we note that 90% of the time, I is equal to the value 10. So what makes sense to do in this case? We pull out the most frequent values. So for example, we check if I is equal to 10, we immediately jump to defaults. Otherwise, we drop into the switch statement. The next optimization is run building. Now with run building, what we want to do is make sure that the most frequent paths fall through. So here I give a list of basic blocks, A, B, C, and D. And again, I order on the edges their relative frequencies based on the profile data. As we can see, the default layout ends up being A, B, C, D in straight line code. The problem with this, though, is that D is called more frequently from B, whereas C is closer to B. And as you probably know from experience, you end up with extra pages being brought into memory, iCache issues, TLB thrashing, etc. So what we can do with profile-guided optimization is note what the optimized layout would be, go ahead and rearrange the code so that it fits into this optimized layout. Separation is similar, except here what we're actually going to do is instead move C into a separate section. And this is a section for very cold code, and you'll have actually code from multiple different functions sitting in this section. The next thing is vcall speculation. So here we have two classes, foo and bar, which both inherit from base. On the right-hand side, we have this function that's going to make use of this pointer to the base class A and do a virtual call on the method name call. So what's the problem here? The problem is in this loop, we always have to go through and do the vtable lookup, and we all know the expense associated with that. If we know that foo is almost always the type of A at that call site, we can go ahead and do something intelligent. So in this case, what we can do is we can check the type of A. If it is foo, we could actually go ahead and inline the method. Otherwise, we go ahead and drop into doing the normal virtual method invocation. And the last set of optimizations I'm going to talk about here with Pogo is partial inlining. So I'm sure everybody is very aware with inlining that we just talked about. Occasionally, though, you have a function that you want to inline, but really you don't want to inline all of it, right? There's cost associated with inlining code. And if part of the code is always cold, it's not called very often, it makes very little sense to inline it. And you can imagine cases, for example, checking error conditions and that type of thing. It's very common in code. So here I give an example where you have a hot code path and a cold code path. And what we can do now with Pogo is, since we can now determine what the hot code path is, we can go ahead and inline that. So we inline that, and of course the cold code path we don't inline, and we have extra mechanisms, if need be, to call the cold code. Additionally, as I showed with the inlining, how I made call site-specific decisions about how to inline, we can also do the same thing with partial inlining. We can make call site-specific decisions about partial portions of the function to inline. So you could actually end up inlining different parts of the same function from different call sites. So now we've seen a set of the optimizations that you can do with Pogo, and you're probably wondering, what does Pogo buy you? In general, performance is going to be application and architecture specific. What we've seen is of the three platforms that we work with, Itanium, AMD 64, and x86, Itanium generally gets the most win, although all the applications get significant win. Additionally, we've seen that large applications tend to benefit more than small. As we've seen, a lot of the optimizations are based on doing good layout in memory, getting the right pages in, getting the right iCache hits, not wasting TLB, etc. In general, though, if you understand your real-world scenarios, it's almost always a win to use profile-guided optimization. And likewise, if you don't understand your real-world scenarios, it probably makes a lot less sense. And it's probably an investigation worth having. So here I give the profile-guided optimization performance over link time code generation, or whole program optimization, another way to say it. So what we see here is on the Itanium platform, for SpecInt, we're getting upwards of 15%. SpecInt around 6%. On AMD 64, we're getting about 10% across the board. And on Intel, it's about 6.5% for SpecInt and about 4% for SpecFP. And again, I should note, this is improvement over link time code generation, which you can view as an improvement on top of normal /02. Additionally, as I said before, the bigger the application, the bigger the win. The Spec benchmark is an industry standard for measuring performance, but realistically, the applications tend to be on the smaller side. For applications such as SQL Server internally, on Itanium, we see wins of about 30% over link time code generation. And on x86, we see wins from the range of 15 to 25%. So I've talked about Pogo. One of the next big things that we've added to Visual C++ Whidbey is OpenMP. And some of you may be very familiar with OpenMP, and some of you may not have heard of it at all. It's actually an open specification for building multi-threaded programs. And definitely, there's the obvious place of wins with OpenMP in the SMP space. But the other place is the space hyperthreading as well. And there, OpenMP can give you a win. Additionally, going into the future, people can begin to start thinking about multiple processors on a core, etc. And these are all places where multi-threading, with respect to performance, is going to begin to elicit large wins. So what is OpenMP? It consists of a set of simple pragmas and runtime routines, the simplest of which is pound pragma OMP parallel. A common technique that people use for developing these OpenMP applications is you start with sequential code and you start inserting pragmas and the appropriate runtime routines into the application. One of the nice things about OpenMP is if you go ahead and compile it and don't throw the OpenMP switch, the application generally runs fine as a sequential application. Everything is nice. You want to parallelize it, throw the OpenMP switch. If you don't have it, the pragmas are ignored. So where is the most value out of OpenMP? It's going to be parallelizing the large loops. And obviously, you want to parallelize loops without loop dependencies. Because when you place the pragmas in OpenMP, it's going on your word as a programmer that there aren't loop dependencies. If there are loop dependencies, most likely the program will generate incorrect results. Or rather, I shouldn't say incorrect. They're correct with respect to what the specification says, but probably not what you expect. Also, you can use OpenMP for non-loop-based applications, but this tends not to be the big win, and I'll briefly touch on it. So here I have a simple piece of code, and I'm going to show how you would parallelize this with OpenMP. And what this is we have two vectors. We're simply doing a vector add from the two vectors to another vector. If you want to parallelize this function, this is all you simply have to do. Pound pragma OMP parallel 4. And now it's parallelized. So what is the compiler doing here to parallelize this? So on the bottom in purple, I now have an example of what the compiler effectively is doing. It has taken the test function and has now removed the loop body out of it and created a new function called test-omp1. Doing this is a process called outlining. You can view this obviously as the inverse of inlining. So we create this outlined function. The compiler also has these OMP helper function routines, runtime routines, VCOMP fork, which then goes and tells the OMP runtime, go ahead and run this test OMP function. It also has inside of it now the VCOMP4 static simple init. And what this is doing is it sets up for each processor which chunk of the iteration space to give it. It ends with the VCOMP4 static end, and then with a barrier. There is an implied barrier synchronization at the end of the parallel for loop. You can explicitly turn that off, though, as well. So if, for example, the value of first is equal to 1 and the value of last is equal to 1,000, you have 4 processors. This simply ends up taking the values 1 through 250, placing them on processor 1, so it will iterate over that space, and then 251 through 500, etc., etc. This is what is known as static scheduling, and this is the default scheduling for OpenMP. OpenMP supports a variety of scheduling mechanisms called dynamic, runtime, guided, etc. I'm not going to go into details here in this talk about the different scheduling mechanisms, but they are varied, and they do allow you to get the best performance for the type of application that you have. You can generally think about the different scheduling mechanisms as a load balancing mechanism. Like I said before, the big win is loop-based codes, but additionally, there is a win with straight-line code. So here I give an example of a function, and inside of this function, we have this if block. Additionally, we have 2 function calls, one to bat, one to baz. So if you will, in this function, imagine these function calls are expensive. They go off and do wild, crazy things and run for many cycles. To parallelize this with OpenMP, you use what they call sections. So you simply take a block, say this is a parallel sections, and then inside of this, you define a set of sections. Again, you're assuming that these sections are independent and that they can be run in parallel. In this case, what OpenMP will do, will generate 3 threads, run them on different processors, assuming you have 3 processors, and then give you nice speed up. Again, remember, these do have to be independent, though. So here we give some performance results for OpenMP. Here I use the NAS parallel benchmark with OpenMP. And these are the HPC industry standard benchmark. And as you can see, in general, we tend to get speedups of between 3 to 4-fold on a 4-processor machine. There is one application where we don't do so well, and we believe this is largely just right now due to our tuning. The reason I do say that is because we've only begun tuning and performance testing of OpenMP right now, internally. We fully expect the performance to even get slightly better. This is a technology we're very excited about and look forward to getting lots of good feedback on it. So here I'll talk about very quickly the OpenMP demo. So in this demo, what I'm simply going to show is what you're looking at on the screen is a grid. And I'm going to be solving a differential equation. And it's actually turned out to not be as complicated as it sounds. You can imagine this grid is a material, and the red around it is heat, and the blue is cold. So you want to simulate heat permeating through the material. I should also say the heat is constant. So you can imagine as this happens, what begins to happen is the interior of it begins to get more and more red as the time traverses. So how do you compute the temperature at a given node in the grid? We use a basic 4-point stencil. So in the middle of that cross is the node we're computing the value of. And the 4 neighbors you see, we simply take the average of each one. And then we iterate across the grid and do that for each point. And that's one time step. And then we do the next time step, and we do it over and over again until we've converged. So here I have this OpenMP solution. And actually, let me make the code window a bit larger. As we see, here is the code to do what I just talked about. It's actually very simple. It's a triply nested loop, but on the inside is the doubly nested loop, which we wish to parallelize. The first time we run this, we'll actually simply comment out the code to parallelize the application, and we will run it. So we do the build, it succeeded. We now go ahead and run it. Actually, also let me bring up the task manager so you can see the number of threads that we use for this application. And it's right there. There's 1 thread, and it takes about 4.8 seconds to run. What I will do next is I'll uncomment out the pragma. That's all we need to do. Now we'll simply go ahead, rebuild this. It built successfully. We'll go ahead and run this application again. And this time, as you can see, it generated more threads, 5 threads in this case. Turns out this is only a 2-processor machine, though. And this time it ran in 3.2 seconds. So it doesn't take too much math to see that we've been able to get relatively large speed up on this application by simply inserting this one simple line. Next, so I know I've been talking about generating efficient code this whole talk, but in particular, let's look at this other issue that often comes up. So here I have a simple function, And the programmer who wrote this function knows that int a and b don't overlap, will never overlap. And so I know several of you are looking at this code right now thinking, okay, obviously the code gen for this is going to be bad. And you're right. This is what the generated code will look like. So as you can see, there's 16 moves that take place here. Now, if you look at this copy 8 function, obviously we have to do the stores into each value of A0, A1, etc. But as you can see, we can do the load of B0 and B1 once, and we shouldn't have to keep on reloading them. But yet the compiler, as you can see, B is EAX, continuously loads B0, B1, B0, B1. So what's the problem here? The problem is we know that A points to the beginning of the A array. So what does B point to? Good question. We simply have no idea. It can point also to the beginning of the A array. It could point to A plus 1. It could point off into space. The compiler simply does not know this information. This is a problem known as aliasing, and it's a well-known problem that probably every C, C++ programmer has dealt with. And especially if you come from Fortran, you know that this is often a Fortran programmer's best friend. As I said before, the issue is you don't know what a pointer can point to. In Whidbey, one of the things we've done, and we think it'll be a big help for developers and code maintainers, is we've removed the OA switch, which is assume no alias. We've tended to find this was a death sentence for developers. Most people, frankly, just didn't know what it meant. Our compiler would add a new optimization where we would take advantage of this. It would break their code in some ungodly way that they just had no idea what was going on. And of course, this often ends up going back to that /O2 issue I talked about. People think, it works great with OD, but I throw O2, and now the code gen is all wrong. It's usually because they didn't understand what this switch meant. We've replaced this now with a more targeted approach. We've added a keyword, __restrict. And this is very similar to the C99 keyword restricts. There is a slight difference with respect to array syntax that, again, if anybody wants more information about, I'll be happy to talk to them afterwards. But what restrict is, it's a promise to the compiler that the address that you point to through a given pointer cannot be accessed by other pointers. And at the bottom, I give an example usage. The restrict keyword modifies the pointer. So now let's look at this example again, the same code, but this time we add the __restrict keyword. Here we now look at the code gen. If you remember last time, there were 16 moves that took place. This time there are 10. What's the first thing that the compiler does here? It takes B0, B1, it then registers B0 and B1, and then continues to use them throughout the rest of the code. It can do this because of the restrict keyword. It knows that B and A don't alias. Now, you might look at this and think, wait a second, you only have restrict on A. It turns out I can do this because A and B are the only two pointers. You can place restrict on one of them, and by transitivity, you know that B won't also access it through A. If you add another pointer, things become trickier. You'd have to add another restrict, depending on actually what alias restrictions you would like. So the next thing is the floating point model. So I know last time I talked about removing OA. This time I'll talk about removing OP. So a lot of people who do work in the floating point space are quite familiar with /OP. And usually what /OP meant was make my code really, really slow if it was floating point intensive. The problem is if you demanded precision, /OP was often the only way to get it. And unfortunately, there was no intermediate switch. It was either /OP or nothing. So now what we've done with Whidbey is we've introduced a new floating point model. This new floating point model, we introduced 4 flags: FP fast, FP precise, FP strict, and FP accept. I'll go into more depth into each of these now. So what is FP fast? Well, this is going to be the switch that you use when performance matters the most. In general, this is also the switch that you don't want to use when you're in the deep corners of the FP world. For example, if your application cares about the difference between plus and minus 0, you probably don't want to use FP fast. If you care about correctly evaluating expressions with NANDs, you probably don't want to use FP fast. Additionally, FP fast can do lots of optimizations, which, depending on your application, algebraically are completely legitimate. But of course, with floating point numbers, you can end up with odd results. So FP fast will, for example, do association. We will do distribution. We'll do factoring inverse, which is where if you're doing, for example, division by 4, we'll change it to a multiply times 0.25. We'll do scalar reduction. So if we unroll loops and we see the accumulations, we can go ahead and perform our own reduction in the compiler on that. And additionally, we can do copy propagation of float values. Now, FP precise is the new default floating point switch. And this we found to be the sweet spot between performance and precision. So in general, performance-wise, we're looking on average, we're seeing about 3% slower than FP fast. So if you demand the extra speed, FP fast is the way to go. But the loss using FP precise really is not that bad. And with respect to precision, we're generally IEEE conformant. The big issue is exceptions. One of the things we will do with FP precise is we will hoist expressions even if those expressions throw exceptions. One of the questions that people, when they see the floating point model, ask first is, how is rounding handled? With FP precise, it's at assignments, casts, and function calls. And depending on the architecture, this sometimes requires the writing of the value from register to memory. This is called homing. And I'll use that term a bit more, so I just wanted to make sure it was well defined. I mentioned before with FP precise that we don't have IEEE conformant exceptions. But you can throw the FP accept switch and get the reliable floating point exceptions. So what does that mean? That means that exceptions are thrown or not thrown when expected. And if you have some experience using x86, I'm sure you know what I mean with exceptions not getting thrown when you expect them to. So on x86, what we will do for FP accept is we will insert the appropriate F weight to get the absolute correct behavior. On AMD 64 and on IA 64, the exceptions are reliable at the hardware level. So with FP accept, what we will do when thrown with FP precise is that we will not hoist expressions that can throw exceptions. I should note, though, that with FP fast, you cannot use FP accept. So if you care about exceptions, you can't use FP fast. Additionally, they're not compatible with /CLR. And this is in part just due to the way we interact with the JIT at the moment. Next is FP strict. And this is the strictest of the FP options. This is the option in general you will want to use when you care about precision absolutely and don't mind a very noticeable performance hit. So here what we're looking at is on the order of low double digits right now. We'd actually like to try to get this into the high single-digit percentage slowdown compared to FP fast. That's a work in progress. So with FP strict, FP accept is implied. So you throw this switch, you get reliable exceptions. Again, I should also note that this, with the implied nature of FP accept, is not compatible with /CLR. So here I give the floating point precision characteristics of these switches for each of the major platforms that we're looking at. So first for x86, the default precision is 53-bit. And when I say 53-bit, I'm referring to the significand. So this is double precision default. With FP fast, we will not home. We may occasionally spill registers to memory, but we will not home for rounding. With FP precise on x86, we will home for rounding, except when assigning to double. The reason we don't do this for assigning to double is because the default precision is double, hence we could eliminate the home in that case. With FP strict, though, we will always home. And the reason we always home with FP strict is because we try to be extremely conservative and assume that the user can really do anything. For example, the user might have changed the floating point precision on the machine. On AMD 64, the default precision is based on the source dest precision. It uses SSE SSE2 on AMD 64 for floating point exclusively. So for FP fast, we decide how to do the conversion based on what will be the fastest. So our compiler has a heuristic. It goes ahead and looks at if you have doubles and floats in your assignment. We'll go through, for example, and count. If I use doubles, I'll have to do less converts than if I use floats, that type of thing. For FP precise and FP strict, it has the appropriate sized operations. So in both cases, with respect to rounding, it behaves the same on AMD 64. And it may not obviously choose the fastest, but it will be, with respect to precision, very concise. And then the last platform, Itanium, uses 64-bit default precision, which is extended double. So if you use FP fast on the Itanium, we won't use a completer to do rounding. If you use FP precise, we will use a completer to do rounding, but we will only do it at rounding points, which I noted were at function calls, at assignments, and at casts. We won't do it at other points. But with FP strict, we will use completers for precision on each operation. You'll probably note, looking at x86, that for the FP strict, I note homing at the rounding point. The problem with FP strict on x86 is homing is so expensive, it can't be done on each operation. So next I'm going to walk through a simple floating point example to kind of give you an idea of what's taking place at each step along the way. So first, if you have this simple code segment listed here, A plus B will be evaluated with the default precision. That's because A plus B are doubles. So depending on what the default precision is for the given machine, that's the precision this expression will be evaluated in. Next, C plus X. X will be promoted up, and C plus X will then be evaluated in the default precision. Now in the assignment, if you use FP precise or FP fast, the final result will be left in a register That is, it won't be homed. Why won't it be homed for precise? It's because the result type is a double. FP strict, on the other hand, the final result will always be rounded to a double. Next, X plus M. With FP precise and FP fast, X plus M is evaluated with default precision. With FP strict, X plus M will be rounded to a float, except on x86, where it won't be. Next, M is promoted up, except on AMD 64. And then lastly, the final result, Z. With FP fast, Z is left in a register. With FP precise and FP strict, the final result is rounded to a float. I know admittedly this is maybe a little bit tough to follow with the differences in the architecture, but I believe you guys also get a copy of the slides so you can go back through and have fun at home, understanding how these all work. So the next thing I'm going to talk about is some of the security work that we've done in Whidbey. So this isn't performance work, but still nevertheless important code generation. So as you all know, GS was introduced in VS7, and this helped prevent attacking the return address. And this was done by introducing a cookie to the stack. You couldn't write the return address and have the stack unwind without the cookie being examined. Additionally, we added safe exception handling. Another possible attack mechanism somebody might use is trying to grab the exception handler. And with safe exception handling, the compiler and the operating system work together to make sure that the handlers are quote-unquote authorized. Again, this is work that we did in 7.0 and 7.1. In Whidbey, we continue to improve. So if we go ahead and we look at the stack here, what we'll notice is that parameters sit above the return address. So we do have the cookie that's sitting in between the locals and the return address and the parameters. But there's clearly another attack that can take place here. Pointer parameters are vulnerable. So what you can do is you can, with a local buffer, overwrite it, standard buffer overrun attack, overwrite the cookie. You don't care what you write on top of the cookie. Go through the return address, and if there, for example, is a function pointer that was passed as a parameter, throw a new address in there. The reason this doesn't get caught by the cookie is because the cookie isn't examined until this part of the stack is unwound. And if this function pointer is invoked during execution of this function, or at some point later down the stack, the cookie is never looked at, the compiler never knows. So what we've done here in Whidbey is we've now taken the vulnerable parameters, the pointers, the function pointers, structures containing pointers, etc., and we move the vulnerable parameters below the locals. So now obviously local buffer overruns can't attack the vulnerable parameters, and the safe parameters stay where they are. And in the same way we did with 7.0 and 7.1, with the insertion of the cookie, we only do this optimization in vulnerable functions. These are functions, for example, that have local buffers. These are functions that are going to do mem copies or string copies, etc. In cases where this does not happen, you don't incur this cost at all. Next, the other thing that we're doing in VS Whidbey is we're taking the C++ optimizer and we're now optimizing MSIL code. So most people, when they think about optimization of managed code, they think about the JIT. You get the MSIL, the JIT grabs it, starts doing optimizations. What Visual C++ has years of experience with, though, is static compilation, static optimization. We've taken all this experience, and now with Managed C++ and /CLR, we can generate optimized MSIL code even before it touches the JIT. So what do? We do pretty much all your standard optimizations. So this includes all the global optimization work that we have, and there's tons and tons of work here. We do expression optimization, and I know I'm biased, but I've seen lots of expression optimizers, and I think the VC expression optimizer is probably the best one I've seen in any compiler. With that said, where does this have problems? The first problem is strength reduction. So you have a loop, you have array accesses in the loop. Standard strength reduction will go ahead and replace the addressing into the array, which is done with multiplies, by pointer arithmetic, usually pointer increment. If you have a GC type now that you're referencing in the loop, all of a sudden that becomes unverifiable. That's a problem. So obviously those types of optimizations we can no longer do. Another place we do have problems is inlining. The CLR has very strict accessibility requirements. And since we're actually doing the optimization at the MSIL level, we must respect all the accessibility requirements of the classes. So we can't go ahead and inline one method into another method if the method that gets inlined into wouldn't have access to the data members. Additionally, there's lots of new types of decisions that have to take place. For example, loop unrolling and inlining again. So there are many opportunities where we can still inline, and obviously opportunities where we can go ahead and do loop unrolling. But now, all of a sudden, we're not generating out of the compiler native assembly code. We're now generating MSIL, which in turn is going to be handed to a jitter, which has to run on somebody's desk. And so we don't want to unroll the loop, expose a plethora of live variables, and then have the JIT have to all of a sudden do register allocation on all this. And register allocation, as you may or may not know, is an NP-complete problem. So doing it well is difficult, and it's difficult for a static compiler to do. Now imagine a JIT having to do it and still be responsive. So we now have to make new types of decisions and make trade-offs about what we present to the JIT and what we do ourselves. There is actually a talk that's going to be given Wednesday at 11:30, leveraging native code with .NET that I recommend people to go to, where if you're interested in these types of things, you'll be able to hear more of it. And the last thing I'm going to talk about is 64-bit code gen. And as you may have guessed from some of the other slides, obviously, x86 is no longer the only desktop server platform we support. So we'll be actually in the PDC bits. Visual C++ has cross-compiler support for Itanium and AMD 64 compilers. When we do ship, we will have Visual Studio that installs on 64-bit. There will be 64-bit hosted versions of both compilers. And the main thing to note here is simply get your code 64-bit clean now. This obviously isn't a 64-bit talk. The main takeaways I'd just like for people to get out of this is that ints and longs are 32-bit, but pointers are 64-bit. And this was done for the very explicit reason of making porting easier. I'm sure a lot of you remember the 16 to 32-bit migration wars, and that was generally a nightmare. What we've seen internally is that moving to 64-bit is magnitudes easier, and we think in part due to this decision to go with 32-bit ints and longs. Now obviously there's going to be problems with this, and if you in the past had lots of code that treated pointers and ints the same, you may end up with problems with truncation. So that's one of the common pitfalls and one of the things to look out for. Additionally, the other big issue that we've seen a lot of people hit is alignment issues. So this is especially notable on the Itanium platform. On the x86 and AMD 64 platform, you could effectively have alignment and you suffer a performance degradation, but it's not huge. On x86, the OS will fix up the alignment fault. On AMD 64, it's actually in the hardware. On Itanium, alignments are visible to the application. So if you don't catch the alignment, if you don't catch the exception, expect to have a problem. And here I'll just quickly go into a quick demo of how to use 64-bit from the Visual Studio IDE. And while none of the demos have exactly been extremely exciting demos in the sense of the Avalon demos, I hope people find this one especially useful, as this is the one that you can immediately just go out with your PDC disks, try, generate 64-bit code. And actually, I should also note, if you go to the Visual C++ booth, you can go ahead and run all these, and we have a 64-bit machine there that you can also go ahead and play with. So here I have a very simple application. Actually, it does almost nothing. And what we'll go to is we'll go to this build here. And as you note, there are different types of configurations. And you can pick Win32, Win64. You can go to the configuration manager. You can go to New, view the different platforms. You can select Itanium, etc. And just simply by making these selections, you can change which platform you're compiling for. Go ahead, let me do a rebuild, because I had probably built this earlier. It succeeded. You could go to the command prompt. This is actually a 32-bit machine, so we can't run it. But as many of you probably know, you can run dump bin, take a look at the headers, and you can note that this is an AMD 64 image that's generated. So it's actually quite simple. And as I said, the migration from 32-bit to 64-bit we found to be quite simple. And we've been able to port relatively large applications in short time. So what are the general takeaways here? The general takeaways are, first of all, with Pogo, understand your real-world scenarios. It's of much less use if you don't. The next thing is, if you want to write multi-threaded applications, especially loop-based ones, OpenMP is the way to go. It's the easiest way to do it with Visual C++. The next thing is note the use of restrict for alias hints, and that /OA has went away. Additionally, the new FP model gives you now both performance and accuracy. We've added better security, and I think we'll continue to see us doing that more and more going into the future. MSIL code gen coming out of Visual C++ will be faster than ever before. And lastly, almost like a call to action, is to make sure you get your code 64-bit clean now. So here's a slide for more information. First of all, like I noted before, there is a Visual C++ hands-on lab where you could go through and play with a variety of different demos and recent bits, actually bits that are slightly newer than the ones that we've given out here at the PDC. But that's a good place to go and have some fun with some of the stuff that we're coming out with. Also, the Ask the Experts is tomorrow, and we'll have most of the VC people there, I think about 10 plus or so. Additionally, you can go by the demo booth at the product pavilion, and there's several VC people there. One of the things I'd like to note is the top priority is talking to you, so if you see people eating lunch or catching a taxi or whatever, feel free to grab them and suck up their time. That's what they're here for. A link to a paper on 64-bit code cleaning, the OpenMP specification, which is available online, and we will be completely conformant with the specification as listed. Also, there are PDC news groups that you can go ahead and post to, and we will be monitoring those during the convention here as well as after it's over with. And lastly, my email. So feel free to go ahead and email me with questions. And that is it. I will happily take questions now. Thank you.
I'm using Microsoft CEO Visual C since 15 years, and I appreciate that the created code becomes faster and faster. On the other side, I see that the compilation speed is going down over 15 years. This is not, I understand that optimized code needs longer time for compilation, but typically 90% is debugging code, and this is so slow, this is so frustrating. I think Microsoft C is now the slowest compiler on the market. What we will do in future to enhance that?
There are a couple of things that we're doing. So first of all, throughput has become increasingly important. One of the features I didn't talk about here was our multiprocessor builds. That is something that we are enabling for Whidbey, so you can use multiple processors to do builds. Additionally, we're enabling a feature called concurrent PDB, so one of the cost often associated with the whole development cycle is often the cost of opening and shutting the PDB. So with concurrent PDB, we're actually creating a PDB proxy and allowing different parts, the debugger, the front end, to all access this proxy concurrently. So we think in general we're doing lots of things to reduce compiler throughput. Additionally, one of the other things we're looking at post-Whidbey is a multi-threaded backend as well. This is one of the things that we've been looking at for a while, and we think definitely post-Whidbey this is something that is right on target. But I mean, we've definitely heard this concern. We track throughput very much. It eventually becomes, so you often have this trade-off, right, between getting this optimization in and getting and less throughput. And it's a tough trade-off. Most people want the better code gen, but like you said, if you're doing development and your builds take 2 hours on upward, NT takes 12 hours on fast machines, right? And you want better throughput than that. So we are noting that, and we are working on that. So like I said, with the concurrent builds, that's something that we think will be a big win.
With scientific type applications, profile-guided optimization can make a great deal of difference because of the small basic blocks. But in a large commercial application, we're talking 100, 600 megabytes, it's really laying out the basic routines in the most common executed order with cache hits that makes the biggest difference, or page faulting. Right. And that doesn't need the same granularity. And it's difficult to have an application like that use profile-guided optimization where each individual compile of it has to be done. Have you any thought to just providing layout of the routines that should be collected together in the image rather than all of the basic blocks, so that you don't need to go through a build, compile, optimize every single build? Just the layout in the image can make a huge difference.
Right. So, there is the ability, for example, with the /order link option to do something similar if you know about this ahead of time. One of the things that we have seen, first of all, with Pogo, our huge win, I'm not sure if you caught this earlier, was like, for example, the wins we get with SQL Server, a relatively large application on the order of millions of lines. Also NT, we also get large wins with. Not quite on the order of 30%, but double-digit wins. So we are able to see that, with large applications, we are able to get big wins. So one of the things also I should note is in the picture, I noted basic block ordering. We also do this at the function level as well, completely independent of the basic blocks. So things are kind of, you can almost view them as like a hierarchy in terms of granularity. So we look at the function level, then we look at the basic block level as well. Does that?
Okay. Can I follow on to the other British guy's comment? When you're doing Pogo optimization, can you pick up other metrics, like disk I/O?
Oh, sorry about that. I didn't. Say that again? I was looking the wrong way.
Back to his point about disk I/O. If you're doing profile-based optimization, can you insert or gather other metrics, not just CPU time executed, but disk I/O throughput?
Currently, no.
Any plans?
Right now, so one of the things that we are doing with Pogo is we're looking at actually a wide variety of additional profile information that we think would be useful. So obviously a big one is going to be disk I/O. We're also interested in looking to see, because as you can see the way the probes are set up on the edges and the value probes, they're at a relatively high level of granularity. We're also interested in looking, okay, what if we actually got down to different lower levels of granularity with architecture characteristics? And the disk I/O is something that you can almost view this as sitting in between those two. So that's something that, obviously, disk I/O is a big one that we're going to be looking at. I can't make any promises about delivering anything like that, but it's the kind of thing that we are considering.
Okay, one little quickie. I don't use GS because it invokes main CRT startup. Any way of getting around that?
Not that I know of, but you know, I can find. Actually, not that I know of, but I can talk to you offline about that, and we can get a definitive answer.
Thank you.
Yeah, you mentioned earlier about how people had shied away from using /O2. I may have been one of the reasons people do that. One of my articles, I referenced some work by Rich Shupak. He had told me that Microsoft internally used /O1 to make smaller executables, thus reduce total paging size. Is that advice no longer correct with the new compiler in /O2?
Right. So one of the optimizations I didn't talk about with Pogo. So first of all, we use Pogo internally. And one of the optimizations that we do with Pogo is we look at hot-cold functions. And we look at the size of the function. And if we have a function that's hot and relatively small, we compile it /O2. As they begin to get bigger or they become colder, they're compiled /O1. If you were to look at a trace of like all the functions and how they're actually compiled, you'd probably see 90% are compiled /O1, right? And it follows the 90-10 rule. And then there's going to be a small set that are compiled /O2. That's pretty much the way it breaks down. So, and I should go talk to Richard about that as well.
Okay, so then the follow-up question is the Pogo stuff sort of the logical outgrowth of that, the RVA mapping that's in the, I forget what it was called. It's in the, there's a special section that mapped, basically when code got moved around, the debug information didn't get updated. There was, I forget the name of it. There was a OMAP.
Okay, I don't think I know.
Do you not know about OMAP?
No.
Okay.
Yeah.
Never mind.
All right.
It sounds like the profile-guided optimizations would work better on large monolithic apps rather than if you had your application built up of a lot of DLLs. So some of the optimizations may not work well across if you have your app built up with DLLs or plugins, and also if you have DLLs that are shared amongst different apps where their usage pattern may not work well or may be different, then you won't be able to optimize well across the different applications.
Right, so that's a correct assessment, right? So Pogo is going to work at the XE level or at the DLL level, and you can generate your profiles using the set of DLLs together that are, that you want to use, but you're not going to get the optimizations across DLLs. And
so in that case, you'd have to rebuild your DLLs along with your EXE as sort of a whole package if you're profiling.
If you want something that's going to most closely resemble what you're shipping, that is the best thing to do. Although it depends on the application, depending on how the other DLLs, affect, the memory layouts, etc. But yeah, I mean, currently that is a limitation.
Okay.
Question about .NET optimizations. One of them is inlining. CLR itself also does inlining. I'm not sure what you're winning by inlining in IL.
So one of the, we can make better decisions, we think, in some cases. So One of the things, actually, again, that I didn't talk about is with Whidbey, we're going to be enabling link time code generation with /CLR. So this is the whole program optimization. And so we think with that, we can make better decisions about when it makes sense to do inlining. That's not, the JIT also does have information we don't have, right? Because the JITs run at, runtime. But
it always has entire program available to it, right?
But it doesn't have the same amount of time to do the analysis, right?
Wouldn't that be moved to NGen?
If you're doing an NGen,
not right now, but I assume in Whidbey or whichever version, it would be moved there, right? So then things you compiled with CLR will only slow it down.
If you're using NGen, then it makes sense, but there's no guarantee, right, when you generate MSIL, that NGen is going to be the consumer of it. So.
Yep. For those of us who have a need to do our own memory management and placement, is ILP 32-bit pointers going to be supported at all, or mixed mode 32 and 64-bit pointers, or are you just going to just 64-bit pointer and IL32?
Yeah, we removed support for 32-bit pointers, and at this time, it looks like we're not going to reintroduce them. Yeah, so that's the answer. And I know people probably, almost every number you see, spec number reported from HP, et cetera, is actually reporting 32-bit pointer numbers on 64-bit, but we are currently sticking with 64-bit pointers.
I have two questions. One is, are there any plans for the compiler to generate SSE and SSE2 code? And can you use those intrinsics with OpenMP?
So the answer to both questions is yes and yes. So right now we already generate SSE, SSE2 code. So if you throw the Arch SS, there's a switch for it. You can throw the Arch SSE, SSE2 switch, and that's actually in 7.1. You can do that now.
I thought that was only to enable the intrinsics.
No, it actually generates SSE, SSE2 code together with x87. So actually, if you look at CodeGen for a non-trivial floating point application, you'll see both. You'll see XMM and you'll see the floating point stack. It also allows you to use the SSE, SSE2 intrinsics, and we do support the SSE, SSE2 intrinsics with OpenMP.
Does the x86 code generator do any better job on floating point to integer conversion?
Say the question one more time.
Does the x86 code generator do any better of a job on floating point to integer conversion? At the moment, it goes through the C runtime library, and there are problems with the way that's done.
There was a word that sounded like vector.
No, x86, the Intel 386, 486, Pentium code generator. Just wondering if it still goes through the runtime library or if you use a direct use of the floating point conversion operations.
Right. So right now, currently what we have, and you said x86. Yeah, so these right now currently go through the runtime. What's that? For the SSE2? Oh, the conversions from floats to ints. Yeah, let me take that one offline to make sure I understand exactly what that question is.
Excuse me, actually. I think, in fact, you already provide a service to avoid the _F2L call, and that's through the /QI FISTP.
To avoid the what?
The rounding integer problem he was referring to.
Oh, right.
Yeah, you have the QI FIST, which uses FISTP and then FRINDNT to take care of the rounding.
Regrettably, that doesn't work all the time.
Right. Well, it depends on your rounding model too, right? You can trigger the rounding model.
In the current release, NGen really does no better job than the JIT. Are you going to fix that so that if someone's prepared to NGen a whole application, who cares if it takes 4 times as long?
Right. So currently, the NGen basically is just the JIT right now. What we're going to do in the future, and I don't know how many people have heard of this, it's the Big Phoenix project. where we're completely changing the compiler backend. And what's that?
IR-based. There's a Microsoft research project on it, right? You can look at it on Microsoft Research, I think, website.
Right, it's a joint project between Visual C++ and Microsoft Research. And so the interesting thing about that is, the first thing they're working on is actually an x86 pre-JIT. And so they're using that, but the basic idea is actually the code base for the static compiler, the JIT, and the pre-JIT will all be the same. What you do is you turn a dial effectively to say, what degree of optimization you want to do, what type of throughput you want, and it basically will spit out a compiler that will do that. So in the future with this Phoenix compiler, the idea is with NGen, you'll be able to get most of the way as you would with a static compiler, if not everything. So if that answers your question, the answer is yes, we do plan to improve it.
So I remember Intel's C++ compiler already have a P0 and OpenMP stuff. So does Microsoft acquires Intel's technology, or Microsoft develop its own technology? If so, what's the difference between Microsoft's P0 and Intel's P0?
Okay, so Microsoft's technology is completely Microsoft's technology. Number one, profile-guided optimization is very tightly integrated into the compiler, the back end. I'm not sure if that's the biggest reason that we didn't, that we're not using Intel technology, but they are very tightly related into it. So that's, probably at least one solid reason that the technologies aren't the same. You also mentioned, OpenMP also.
Yeah.
Our implementations are also completely independent. Again, with OpenMP, it's very back-end, actually back-end and front-end with OpenMP. I guess in theory, you could say we could use the runtime. We could share the runtime. Currently, we don't share the runtime either. So we have our own front-end, back-end, and runtime for OpenMP as well.
So will VC win the Intel's compiler?
What was the question, one more time?
Yeah, will VC beat Intel's compiler?
It depends
on
on
performance.
So it depends, I think, a lot on the application, right? So, Intel, their compiler is really geared very well towards spec, in part because spec sells chips. Our compiler runs, I don't think there's, in fact, I'm pretty sure there's no compiler on the planet that runs more code through it than we do. So I think we tend to have a very stable code base, and we also do very good at generating smaller binaries than Intel. So it's dependent on what you're looking for the compiler to do.
Especially with C++, if you run that through the Intel compiler, you can end up with 4 times the code and 30% performance hit. It's not really their area they've optimized well. And quality is certainly suffering if you look at all the patches that come out. I mean, I wish they got better with it. We spent 6 months with the Itanium compiler trying to get it to work, and so far it's pretty dire.
All right. Have you used our Itanium compiler?
Well, only at the November 2002 level, and it's highly unoptimized, so it's not really ready for production.
Wait, do you remember the number on that?
Well, it was the platform, whatever comes out with the platform SDK.
Okay.
And that hasn't been updated since like November 2002.
Yeah, there is. If you're still using it, I can get you information on an updated version. Actually, there's some nice floating point work that's also went in. So.
This question isn't specifically about the compiler, but it's about how certain system APIs work. If they would have default 16-byte alignment, so that for memory blocks that come back from them, such as div sections, could be used with SSE or SSE2 instructions.
Or are you asking if they do?
If there's any plan to do that, to make that like a default, so it would be easier to use those instructions with the like GDI calls and other memory blocks that come back from Windows APIs.
That's a good. So That's a good question. I mean, certainly I've seen nothing to do that for x86. For AMD 64, the stack is, for example, by default 16-byte aligned. I'm trying to think now, like, for example, what by default, malloc will return. And off the top of my head, I can't seem to recall if it's 16 or 8-byte aligned. So to answer your question, for x86, I certainly see no work in that space in particular. For AMD 64, they are doing, in general, alignment on 16-byte boundaries.
So otherwise, you have to use those specific keywords to align a memory block. There's
Right, so you'll use the decl-spec aligns. Also, there's like the aligned runtime routines as well. So you have to do those types of things for right now for x86.
And just one little hint for people on the 64-bit stuff, if you use a set jump, long jump buffer, it actually is 16-byte aligned, but you might put it in the middle of some other structure that you use malloc with, and malloc comes back 8-byte aligned, and then everything gets an alignment fault. So there are certain things you've got to be careful with these 64-bit machines that may not be obvious, that use more alignment than you expect. And if you've got a structure inside your C code, you're fine, or C++. If you've got a structure that you actually malloc, you can really get shot quickly.
Right.
So do you have like a cheat sheet for how to do this?
I have a question regarding the OpenMP stuff. Does this stuff also on a NUMA technology to make sure that they are not going over the crossbars if it's not sufficient to do so?
Right, so a couple of issues here. So the biggest issue is that the OpenMP specification gives you nothing with respect to NUMA 2.0, and this is obviously one of the big things on futures for the OpenMP Architecture Review Board. With that said, one of the things that we are investigating is processor affinity and trying to figure out if we can do smart things with no information effectively. And like I said on the slide, we've really just begun the tuning. So what we've done is we've implemented the spec completely, so and we're able to get reasonable performance. And right now we're about to start throwing all of our test suites and actually, pulling up all the different HPC test suites as well and start seeing, okay, what are the smart things to do to get us the right performance? And, things like processor affinity and making sure that you're doing the right thing, especially on a NUMA-based architecture, where if you get memory from the wrong place, it costs dearly. That's something that's going to be very important. I can't guarantee that we're going to have a solution, though, but it's something that we're very aware of.
Okay.
Any other questions?
This isn't actually a C++ question directly, but indirectly, in the sense of what is the future of MFC with Longhorn and Avalon and all that? Is it going to continue to be supported? Is it going to be classes added to support the new functionality in Longhorn, or is it basically going to go the way of WTL?
So there's actually a talk here at this session given by Anson Sao on MFC and Longhorn. Unfortunately, I don't know the session number, and I'm pretty sure he has not given it yet, because I think he's doing it on the same